started from where we left off last time. I think so. Last time we talked about the series resonance. We covered that. I just want to go back to one quick point again, and then we move forward. So when we were talking about quality factor, I wanted to just tie some physical significance into it. I think I tried and I failed last time, so I want to give it another try. So in series resonance, the equivalent circuit we were dealing with was a source, right, at a specific frequency, and we had an R, L, and a C circuit, right, in series. And the objective was, at resonance, V output, we wanted to maximize V output, right? So this was a certain resistance. At resonance, we wanted to maximize V output, meaning if I think of a filter from a filter's perspective, it's like I would like to make this one single frequency pass through with a high magnitude, right? That's what I would like to do. So so this is my source. It can have many frequencies, right? So that can be a combination of frequencies, or it can be a single frequency, right? If it's assuming for simplicity, it's a single frequency, which is my resonant frequency. What happens at the resonance frequency? The current is going to equal the impedance divided by the voltage divided by my impedance. The impedance is equal to what? R plus j omega L minus 1 over minus j over 1 over omega c. What happens at resonance? If I want to maximize my output, we said that j omega L and minus 1 over j omega, this difference is 0, right? So we're left with the resistance only, so the impedance to voltage, which pushes current to the circuit, decreases at that specific frequency only. Okay, so and we want so before at the frequency that is not the resonant frequency, what do we want to do for a signal that is not the signal we want to pass through? What do we want to do to that signal? Attenuate it as much as possible, block it from passing through. So we would like at the non-resonant frequencies to have this effect of this inductance and capacitance, or this impedance, very large. Maximize the effect as much as possible when we are away from the resonant frequency, and then at the resonant frequency have the impedances, this L and C impedances, disappear. Right? That's the objective here. So we would like we would like we would like the inductive impedance, right? What happens to inductive impedance at resonance? It equals the capacitive impedance, and they both disappear. At non-resonant frequencies, we want it to be as large as possible, right? So the quality factor is basically this 2 pi FL, so it's the omega L. It's the inductive impedance over the resistance. The resistance is what we're left with when the filter is at resonance, right? So we would like the omega L, this impedance, to be as large as possible, right? So that's the quality factor, or is an indication of how good of a job you're doing, right? So I would like this impedance to be as large as possible, because at resonance it disappears. So I would like the difference between the non-resonant and resonant performance of the circuit to be very significant. So I would like to attenuate very well when I'm away from my resonance, and I would like to pass the signal without any impedance when I'm at the resonant frequency, right? So that's why this 2 pi FL or omega L, I would like it to be, that's why it's in the numerator, because it disappears at resonance, right? So it has to be very big. The quality is this being as large as possible versus the resistance. Does it make sense? This is for series resonance. So how about for parallel resonance? Now that you understand this, we will look at what the quality factor definition is for parallel resonance. But in parallel resonance, we have the components all in parallel. So what do we want to happen to the L and C at parallel resonance? We want them to become what? Versus the R. So at resonance, this I wanted away from resonance. This is very large. How about this away from resonance? Away from resonance. At resonance, this will go away. This will go away. Right? So remember, these are parallel to this. So parallel impedances result in a lower impedance than the single than the impedance by itself, right? So I want something the opposite to happen. I would like these to be what? Huh? I would like the quality factor to be these impedances as what? As large as possible, or I want it to be R over, let's say, XL, for example. If it's R over XL at, and this XL is very large. If this is large, what happens to the quality factor? Quality factor becomes small, right? So I would like this to be as small as possible, meaning so at resonance is omega, this omega L disappears, right? So away from resonance, I would like to come up with a physical interpretation for the quality factor. Quality factor for series resonance, it makes a lot of sense that it's the ratio between the XL, inductive impedance, over the resistance. Because the larger the quality factor, what does that mean? It means that the larger I have a large inductance in series with the output when I'm away from resonance. Here, what does this tell us? It tells us that if I'm in parallel resonance, I would like to maximize this. If I maximize this, so before I had current going here and here, right? Before I had current going into the L and into the C. If I make the L and C impedances the same, the current will all go through this resistance here. So it makes a lot of sense that I try to maximize R versus XL, because XL will disappear. These will disappear at resonance, right? So if they disappear at resonance, what is my quality factor? The quality factor is the gain or the output voltage versus the input voltage, right? I would like to maximize my output at a certain frequency. How do I maximize the output in series resonance? I make this and this disappear so that the current multiplied by the resistance is as high as possible. So when they are in the circuit, I would like to make sure I measure quality by XL over R. If this is very large, at resonance it disappears, right? If at resonance it disappears, I'm left with only resistance. If I'm left with resistance only, then the output is the current multiplied by the resistance, and it's maximized in that case. I don't know if I'm making sense or not. Let's look at the equation in the next step. But at least for parallel resonance, for series resonance, you understand why it makes sense that if I have a large impedance, the quality factor, for a large quality factor, I would like this as large as possible when the system is not at the resonant frequency. If this is very large, at resonance it disappears, right? This XL disappears. If it disappears, I'm left with only the R. So there's a big difference between what happens at resonance and non-resonance. So if you go back to our, curves of V output over V input, right? Our objective is to maximize V output over V input at the resonant frequency. This was my resonant frequency. The objective was to maximize V output over V input over the resonant frequency. And when it's not the resonant frequency, I would like to attenuate the signal. right? This is my resonant frequency. I have my source here, L, R, C, right? This is a source at supplying the voltage at some resonant frequency. I would like at the resonant frequency to have as much of this voltage go to the output and be amplified by the value of the resistance. So I will take the current multiplied by the resistance, that's V output, right? The current multiplied by the resistance is my V output, correct? V output over V input, I would like to plot it. At the resonant frequency, the L and C go away. If they go away, that means current will increase. Current increases at its maximum point at the resonant frequency. So I take that current multiplied by the resistance and I get the highest value of my transfer function. Does it make sense? Does this point make sense at least? At resonant frequency, I get the highest current. Current multiplied by the resistance is voltage. So is my output voltage. So if this is my highest current, multiplied by any value of the resistance, it will be my highest output voltage over input voltage, right? So we agree about this point. How about the rest of the system? The rest of the system, the L and C do not disappear. They are there, right? They exist. And they cause an impedance to the increase in current, because current is equal to voltage divided by impedance. So they are, if the impedance is higher, and current is lower, then the value of output voltage, which is the current and the resistance, is lower. So, and if you plot it for specific values of L, R, and C, it will look like this. The output over V input, it will be, for this is one case, this is a second case, this is a third case. Right? What is the difference between these three? The difference between these three is this is a lot sharper rise and fall, right? This is a lot sharper rise and fall than this outer one here, correct? What is happening here? A lot sharper means a more significant change between the condition at resonance and the condition without resonance. So, without resonance, what am I doing? I'm attenuating as much as possible. What does this mean? It means that I have as big an inductance as possible, which decreases the current. Right? Yes, ma'am. For the parallel resonance? For the series resonance? I want the capacitive impedance to be as big as possible, so the capacitance will be as small as possible, yes, because it's in the denominator. I'm talking about an impedance, yeah, XC or XL. Yeah, so yeah, it will be in the denominator for this one, yes. So I would like either the inductive reactance to be as large as possible, or the capacitive reactance to be as large as possible, which means the capacitance as small as possible, right? Because it's in the denominator here. Both this and this, if the capacitor is small or the inductance is large, it will increase quality factor Q, right? Which will increase the difference between what happens at resonance and non-resonance. So if there is a difference between what happens in resonance and non-resonance, if this difference is large, that means that I have a higher quality factor. So I'm maybe around, I'm looking at this envelope of performance for the circuit. Versus if what's happening at resonance versus non-resonance is not very different, then I'm looking more around at this performance of the circuit. Does it make sense? No? Does it make sense? Or really? Or you're just complimenting me? Okay. So this is quality factor. So this is series resonance. How about parallel resonance? So again, what we did here was just write out the transfer function. V output V over V input. V output is I times R. V input is I times the full impedance. Right. So this is V output over V input, and they actually plotted it for different values of R, L, and C for different L and C values. So if I'm changing the L and C values, I can sort of rewrite it in terms of Q, quality factor. So the derivation of how to derive from this equation to this equation. You don't need to understand it, and you don't need to go through the derivation. Right? I mean, knowing this is this is something you should know, right? It's a transfer function is V output over V input. V output is IR. V input is I times the full impedance, and that's what we have here. They just rewrote it in terms of quality factor and resonance frequency F naught to simplify matters for you. Because then I would like to, then you will, if you want you will typically be asked to design a filter with a quality factor of 10, for example, and the resonance frequency of so and so. Because this is what you really want in the application. You would like to amplify a signal with a specific frequency, and you want to make sure that you attenuate everything else around it very well. So you will be selecting quality factor and resonance frequency. Quality factor and resonance frequency, you can relate those to the values of components in the circuit, the L's and C's. R is typically your load. Your load is typically a defined thing, right? You want to feed a specific load. The specific load, you want to feed it with a filter or a resonance circuit with a certain quality factor and resonance frequency. So you'll be given R, you'll be given, for example, resonance frequency, you will be given, for example, quality factor, and then you'll be asked to calculate L. And then you can use the same givens to calculate C. And hence you can design your series resonance circuit. Right? That's how you would go about it. Any questions? Yeah. And we talked about, again, the distance between the half power frequency here and here. This is called the bandwidth of this filter response, or bandwidth of the transfer function response. And you can calculate the minimum and maximum half power frequencies by taking the resonance frequency and adding half the bandpass frequency to it. Any questions on this? We're okay? We repeat the same. So this is an example. The example I think we went through the example last time. Here you're given a circuit with specific values, specific parameters, and they're asking you to find the resonance frequency. So substituting this resonance frequency equation, find the half power frequency. So you first need to find the bandpass first to do that. So to find the bandpass, you will need to calculate the quality factor. So first you calculate the quality factor, given your L's and C's and R's, you calculate a certain quality factor, then you're able to calculate the bandpass frequency range, and then your half power frequency part. Just substituting in the equation. You have to understand. The physical significance is what you need to understand. Any questions on this? Another example, the continuation of this example, I think we went through. Again, at resonance, we know that the L's and C's go away, so the current is equal to what? This voltage, 1 angle 0 divided by 100, so it's 0.01 angle 0, right? No changes in that. So that's the current, that's what they calculated here, and they wanted to calculate the voltage across all the components at resonance. So you take the current and multiply by the impedance. Current multiplied by the impedance. Current multiplied by the impedance for the resistor, the inductor, and the capacitor. Any questions on this? No? Parallel resonance. Before we wanted, in series resonance, we wanted the inductors and capacitors to basically look like short circuits and they disappear. How about here? Here we want them to look like open circuits because we would like no current to pass through the inductor and capacitor and be left only with the resistor. Right? If no current passes in this component and this component, then all the current will pass through the resistor. If the current passes to the resistor, then you're able to, all the current passes to the resistor, so all the source current passes to the resistor, then I've maximized my output at that frequency. Right? Does it make some sense? Before we wanted them to be like short circuits, here we want them to be like open circuits. Okay? And so what is this current, this total current equal to? The total current is equal to what? If this was a voltage, it would be the voltage divided by this total impedance, and I can use the current divider rule. But what is the total impedance? These are three components in parallel. So how do you add impedances in parallel? 1 over Z equivalent is equal to 1 over Z1 plus 1 over Z2 plus 1 over Z3. 1 over Z1, so this is, if you bring 1 over Z, this is Z equivalent. 1 over Z equivalent here, and then it's 1 over Z1, which is the resistance, 1 over Z2, which is 1 over J omega C, and then 1 over Z3, it's 1 over J omega L, it goes up with a minus sign, and we're left with this in the denominator. Right, so this is my impedance. What do I want to happen at resonance? At resonance, I want to make sure that my capacitive impedance and my capacitive impedance and my inductive impedance disappear, right, equal each other. And this, and if you solve, I mean, basically, I would like only to maintain the resistance. Right? I only want to maintain the resistance in the circuit. So if this goes away and this goes away, then Z equivalent is equal to R. Right? Because this goes away, 1 over R, R goes to the numerator, I'm left with only a resistance that is seeing the current coming in from my supply. Right? So this condition is satisfied if these two are equal. These two are equal at a certain frequency, which is the resonant frequency. If we solve for the frequency, it's 1 over 2 pi square root of LC. This happens to be the same equation for resonant frequency as the series resonant circuit. So, same issue. I would like to maximize the current at the resonant frequency. Right? I would like to make sure that the resistance is much bigger. Right? These are in parallel. Right? At the resonant frequency, L and C will counter each other, they will disappear. Right? So what is my measure of quality? It's maximizing the value of my resistance, because this will disappear at resonance. So if this disappears, it becomes 0. Right? If this disappears and becomes 0 because it cancels itself out with the capacitance, then the larger the resistance is versus the reactance that I have in the system, then the higher quality I have of a filter, the higher quality filter I have. And of course, with the capacitance, if I substitute, if I solve for L here and substitute in this equation here, I can rewrite the equation of quality factor in terms of capacitance. So I have quality factor, and I can write my transfer function. Remember, my transfer function is my output voltage versus my input current in this case. Like I'm trying to maximize my input current signal versus maximize the amount of input current signal that goes to the resistor. That's my output is my V out, which is I times R. My input is my input current here. So my transfer function is this. There's no need to derive, again, you do not need to derive this. You will have this equation for parallel resonance, this equation for series resonance, and what you will need to know is you're maximizing, again, this is R times I here, which is the output of the circuit at resonance. This is a parallel resonance circuit. So this is V output, and this is I input. V output is equal to R times the current that's in the resistive current branch, in the resistive branch. And this at resonance, these two will cancel the effect of each other out, meaning there will be no current coming from the source to these. So why is it? I mean, if you remember maybe actually, I'm going to go too far back. If you look at the example that we just did here, We do the phasor diagram here. At resonance, what was the voltage across the inductor and the voltage in the capacitor were opposite by 180 degrees. Right? What does this mean? Right? It means that in one half cycle, if this is a sinusoidal signal, it means that in one half cycle, the voltage and current in a capacitor are in a certain polarity. In a capacitor, a certain polarity, right? And in the opposite, so this voltage is trying to explain. If this is inductor voltage, VL, capacitor voltage will look like this in the half cycle, at the same time, right? They will be 180 degrees out of phase. If they are 180 degrees out of phase, so this is my resistor here, and this is my LC combination. This LC combination, if you push a current into the circuit, the corresponding voltage, right? If I have a current flowing through the capacitor, I will get a voltage across the terminals of the capacitor, right? VC equals IC dVc by IC equals C dVc by dt, and VL is equal to L di by dt. What is the inductor voltage equal to? L di by dt. What is the capacitor voltage equal to? Vc is equal to 1 over C integral of IC dt. Right? So let's say I push a certain current through this capacitor and through the inductor. Like if I push certain current through the capacitor and inductor, what will the corresponding voltage look like? I push the same current. If I push the same current through the capacitor and inductor, what will the corresponding voltages look like? The voltage across the capacitor will be the integration of this curve. The voltage across the inductor will be the integration of this curve. So let's say I have a sine wave. That is my current. If I differentiate, I shift by 90 degrees. If I integrate, I shift by 90 degrees in the other direction. Like it's a sine or a cosine. The derivative of sine is a cosine, the derivative of cosine is a minus sine. Right? So I'm either shifting by 90 degrees in one direction, shifting by 90 degrees in the other direction. Right? So basically, if I do this, so one is shifted by 90 degrees in one direction, one is shifted by 90 degrees in the other direction. That's the corresponding voltage at the terminals of this circuit now, due to the current that I've injected, assuming you're able to inject this current in there. So if you're able to inject this current in there, and the result of that is a terminal voltage across the capacitor that looks like this, blue, and a terminal voltage across the inductor that looks like this, red, then what is the terminal voltage across these two nodes here? 0. Right? You have two voltages that are opposite in polarity, that are opposite of each other, across of each other. Right? Kirchhoff voltage law around the loop is 0. This voltage should equal this voltage. Right? So the sum of these two will be 0. Sum of the voltage across. So it's as if they are not there. If they are not there, it's as if I have all the current flowing through the resistor only. Assuming I'm able to force this current from the beginning. Does it make sense? Okay, so the transfer function for parallel resonance is the following. The example is very similar to the previous example, and it's the same discussion about bandpass frequency and upper and lower half power frequency points, right? But I think the bandpass, it's in the previous case it was I think the resonance frequency, it was the quality factor over resonance frequency. Here it's the opposite. The bandpass for the series resonance Bandpass for the series resonance. It's resonant frequency over the quality factor still. So let's see. Let's look at the example. I mean, you won't find this very different. I mean, the example is very similar because it's a direct substitution in the number. So let's see what they're asking for. They're asking for, you have, again, what you're typically given is what? In an application, you want a signal, you want to pass a signal through at a specific frequency, right? That's typically what you're given. This specific frequency will be what? Your resonant frequency, because that's what you want to see at the output. So you will typically be given your resonant frequency, right? And you typically will know your load. Your load is something, for example, it's you would like to only pass the signal, if you're measuring, for example, temperature changes, right? If you're measuring a temperature change due to a certain physical system, and this physical system changes, you know that this physical system that you're dealing with has two things that change temperature. One changes temperature quickly, one changes temperature slowly, right? And you only want to see the effect of the one that changes temperature quickly. So you will design a circuit that allows the temperature changes due to the one that changes the temperature quickly to pass through. So the resonant frequency in that case will be what you want to see, right? And you would like to take that into a computer. Computers read voltages and current, right? Voltages, right? They read the voltage. So you would like to take that after it passes through your circuit, your resonant circuit or bandpass filter. You would like to measure that, and you want to make sure it's a certain value. So you will take that current multiplied by a certain value of the resistance. So you know that this current will not exceed a certain value because your sensor's capability is known. So you would probably choose a resistor to match your computer's maximum voltage input. So typically you will also know what the resistance are. So you will know your load. Your load is either your computer, or your load is going to be some circuit that turns on a light bulb. Then you cannot turn on the light bulb with a voltage greater than a certain value, or you will burn it, like any other electrical equipment. So instead of giving you the quality factor now, they give you the bandpass frequency range, a bandpass range. Because again, if they give you a bandpass range, it's an indication of the filter's quality as well, right? If the bandpass is very narrow, what does that mean about quality factor? High or low? If the bandpass is very narrow, meaning you're only allowing very limited amount frequency of signal to pass through. What does that mean? What does that say about the quality? High quality factor, right? So they can either give you the quality factor or the bandpass frequency range, right? And here they're telling you that the source current is 1 milliamps at an angle 0. They want you to draw the phasor diagram, show the currents through each of the elements. Okay. This is the current that is going through the circuit. If the current at resonance, the circuit is resistive only, so we know that the output voltage or the current and the resistor will have the same phase as the current of the input, right? Let's solve the problem. So first they want to calculate, so what do they want us to do? Draw the phasor diagram showing the currents through each of the elements in the circuit at resonance. So I'm not given L or C, right? I would need to find L and C. I'm given bandpass, so from bandpass and my resonant frequency I can calculate quality factor. From quality factor I can calculate L and I calculate C. After I calculate my L and C, I can calculate my XL and XC, of course. But before that, I can also calculate my current. My total current at resonance is going to look like what? Since at resonance, my ZC and ZL are equal and opposite, they disappear, then my output voltage is equal to my current times the resistance. The current is given 10 milliamps, angle 0. The resistance is 10 kilo ohms, 10 to the 4, so the output voltage is 10 angle 0. This output voltage is what dictates this output voltage is passing through a resistance. So what is the corresponding current? At resonance, this current is equal to the output voltage, which is 10 angle 0, divided by the resistance. This output voltage is also placed in parallel with on the inductor and capacitor, right? And the inductor and capacitor are still there in the circuit. they just have currents that are going to be opposite in direction from each other, right? So if the currents are opposite in direction from each other, one will be pushing current into the other, basically. So these two currents will be opposing each other, basically. So if the two currents are opposing each other, then the sum of the currents that are going into this node is 0. Right? If this and this are equal, and if this and this are equal, then the current coming in here is 0. So if I would like to find the voltages and the currents at the resonance, I can do what? Given I know my voltage. This is the output voltage is still. It still exists across my parallel resonance circuit. My parallel resonance circuit is R, L, and C. R, L, and C. At resonance, I still have the output, right? At resonance, all the current is going here, right? But this voltage, the output, is also across this L, and also across this C, right? What is the corresponding current that it's causing in this L and C? Again, VL is equal to L di by dt. Current in the inductor is equal to I is equal to 1 over L integral of v dt. Current in the capacitor is IC equals C dVc by dt. This V and this V are the same. They're all this V output, right? This V and this V are the same. I'm taking this V and differentiating it one time. I'm taking this V and integrating it one time. So these two currents, the current in the capacitor and the current in the inductor, are 180 degrees of opposite of each other. So when one is positive, one is negative. When one is positive, the other is negative. So the sum of the currents going into this combination is 0, because the capacitor's current is like this, inductor's current is like this. So what is the sum of the current? So this is a node here, and I have a capacitor here, and my inductor here, right? And I know my capacitor current and inductor current. My capacitor current and inductor current look like this. They are equal and opposite of each other. So this the capacitor current and the inductor current is 0. So the capacitor current. So what's happening at this node? The input current, I input, is equal to IC plus IL. Right? This is coming into the node, and these are coming out of the node. I don't know, can you see? So at Kirchhoff current law at this node, whatever's coming into the node is equal to whatever's coming out of the node. What's coming out of the node is IC plus IL. IC plus IL instantaneously are 0. So what does that mean about what's coming into the node? 0. Does it make sense now, hopefully? So all of the current is going through the resistor. So any questions on this? Seriously, no questions? Was it clear? I don't know. Sometimes I feel like I'm confusing you a bit. Yes? No? It's okay? So we'll start the next chapter, but we will not spend too much time. So next we will do chapter 14. Chapter 14 is about op-amps. So op-amps is sort of a continuation of more circuit analysis versus doing the logic gates chapter. So we decided to do the op-amps chapter first. Operational amplifiers are an extension actually of what we did in the filters. So what we did in the filters was we saw some circuits are able to do, amplify, for example, what's coming in, or attenuate what's coming in, right? There is a certain gain and certain phase response to between input and output. But in these circuits we had these resistors and capacitors everywhere, right? and these resistors and capacitors, and all the signal's power is actually passing through the RC circuit in both the low-pass filter and the high-pass filter. And I was not able to actually look at something with a controlled gain. Let's say I wanted to multiply the input signal by 2, or I wanted to add 2 signals together. Things like that is not very easily done with simple passive circuits. So what op-amp circuits do is they allow you to do many things. Like they can allow you to add signals together, subtract signals from each other, amplify signals, filter signals, but without dependence on the input. For example, in the RC circuit, in my RC circuit that we had for the low-pass filter, for example, the low-pass filter circuit looked like this. This was the input, and this was the output. Current was going in through here, right? I have to have enough current such that the voltage drop here, right? What do you see at the output here? It's the voltage across the capacitor, right? For voltage to reach the output, current has to flow. Current will flow, and there will be a corresponding voltage drop across this resistor. I mean, there's a power loss, right? How about if I would like, which means that the voltage at the output here is always going to be less than the voltage at the input. In the best case, it will be very close to it, but what if I want it to be greater? I cannot. With this passive circuit that we've studied before, I cannot do that. What if I would like to actually have an output voltage that is equal to the input voltage plus 1 volt? Not possible to do stuff like that. What if I would like the output voltage to be equal to negative of the input voltage? Not possible to do stuff like that with passive circuits that we've studied before, right? So, and that's what op-amps do. Op-amps are an electronic device that allows us to manipulate the circuits in many different ways. I can manipulate the circuits by making the output greater than the input, lower than the input, add signals, and I can do that without dependence of the input's power. So in the circuit that we had here for the low-pass filter, the power supply, or the source here, had to have enough current to supply this circuit so that the voltage drop here is not significant, so I can see an output voltage, right? But what if this circuit, this source, is not able to supply enough power, right? Here, remember, power is equal to what? V times I. So sometimes I would like to have a measurement circuit, for example. So, some people that you would like to measure, for example, the oil and gas. You send, for example, big acoustic waves. You vibrate the earth, and you vibrate the earth, and you have these sensors, geophones, on the surface of the earth or in the water, or strung by streamers that are measuring the mechanical response of the earth to the vibrations that you've created, right? And they're measuring that with a sensor. This sensor has an output voltage. This voltage you would like to measure, but this sensor is actually not supplying power, right? So you would like to measure the sensor's voltage, but the sensor is not capable itself of supplying a lot of current, right? So I want you to differentiate between voltage and current, right? If the sensor is able to supply, is going to generate a voltage that is proportional to a physical phenomena, you would like to measure that voltage, but you do not want to have a sensor that is able to supply power, because it's not able to supply power. It's just sensing a signal and creating a certain voltage. So the circuits that we had before, these passive circuits, they require your sensor here. If this was your sensor, or the source is the sensor, this sensor has to have a sufficient current to be able to supply your circuit, your passive circuit, because there's a power loss associated with this. There's a voltage there's a current that needs to go through this capacitor to charge it to a certain level, right? Your sensor should be capable of doing that. What if it's not? If it's not, you have to resort to something that you put between your sensor and your output below it here, which is your computer, that is able to do this amplification or filtering or whatever without consuming a lot of current from your sensor. And this is what op-amps mainly are. So this is this chapter about op-amps. So next class we'll basically do the op-amps chapter. Any questions?